Welcome everyone, and welcome to this tutorial that I will cover one question from three-phase. The other question will be from the magnetic circuit. So let's start with the three-phase question. So in this question, we have three loads. The first one to the right, I will call it load number 1. It is an electric heater. Electric heater, as we mentioned before, this is more of a resistive load. So the power factor has a unity power factor, and we know P. P is 12 kilowatt. The second and the third loads are induction motors. We didn't cover it, induction motor yet, but we'll cover them by the end of this term. So those are inductive loads, heavily inductive with low power factor. Now, the motors are giving in horsepower, 15 horsepower, 12 horsepower, and 1 horsepower is actually equal to 746 watt. So this is like a constant. It's well-known relationship. And these three loads are connected, of course, in parallel, and we are supplied by a source with 60 hertz. And the line-to-line voltage is 440 volt. Now, once we don't know the connection of the load, the only information we have access to it is actually the line-to-line voltage. Then we have, I mean, this is a typical question in three-phase. So these are the typical requirements in a question. A, find the total P, Q, and S that is consumed by these three loads. So these are three loads at different power factor. At the end of the day, we want to know how much total P, Q, and S that is needed for these three loads. Second, what is the total power factor? You'll find that B and A are tied together. Once you know A, you can find B right away in one line. Then power factor correction. If I want to improve the power factor, whatever the power factor, we'll find it here to 0.95 lagging. Okay, we want to know how much Q, how much reactive power from that capacitor need to be added. Then we want to find what is the capacitance. So if that capacitor bank that I will connect is in Y, how much C, the value in C. And finally, I want to find the line current before and after adding the capacitor bank. Okay, so let's start. So this question, basically, the first part, and even if I don't ask you explicitly to find P, Q, and S, that is usually your first step. You always want to find what is the total P, what is the total Q, and what's the total S. Then you can find everything in this specific system. So I will start with load number 1 here. So this is load number 2, and this is load number 3. So I will find P1, Q1, P2, Q2, P3, and Q3, and then we will add them because, as we know, the P, the real power, the Q, the reactive power, are scalars. Now, the major thing that we'll be using to solve this is the power triangle. The power triangle relates the P, the Q, the magnitude of S, and the power factor angle. So if I know 2, then I can find the other 2 quantities. So let's start here. Start with the three-phase heater. So P1 is already given to us, and it is equal to 12 kilowatt. Now, we know that it is a unity power factor, means that the angle is actually equal to 0. When you look at theta, if theta is equal to 0, basically your S and B are the same, and Q is equal to 0. So even by just looking to the power factor triangle, you can figure out that if this is a unity power factor, angle equal to 0, so it means that your Q is equal to 0. So Q1 is basically equal to 0. Then we move to P2. Now P2, we are giving the power as a horsepower. So I need to convert the horsepower into a watt. So basically it is equal to, the horsepower is 15 times the 746 watt, or 0.746, to convert that directly into kilowatt. So this will give me 11.19 kilowatt. Now I know the power factor, it's 0.6. Okay, so I can find the angle. The angle for this is basically is cosine inverse of 0.6. That is my theta. This is my angle. So, and I can find Q from P using the tan theta. We know that Q2 is equal to P2 times tan theta 2. P2 we already know it, 11.19. Tan, what is theta? Theta is basically cosine inverse of 0.6. This is your theta 2. And when you calculate this, you will find this equal to 14.92 kVAR. Now we move to the third load, which is we will have the same approach as the second load because this is we have the same inputs. So your P3 will equal to the 12 horsepower times the 0.746, and this will give me 8.95 kilowatt, and Q3 would equal to P3 tan theta 3, which is equal to P3 is I already calculated 8.95 kilowatt. Tan theta 3 is cosine inverse of 0.72, and this will give me 8.63 kVAR. Now, since our power factor is lagging, the Q will be all plus. Okay, and that is the nature of the load. It's unlikely to have a leading power factor. Just in case for an odd reason you have a leading power factor, then the sign of Q will be negative. That is the only thing that you need to pay attention to. So now we found P1, P2, B3, Q1, Q2, and Q3. Then we will go and find the total P. So your P total for the three loads is equal to P1 plus P2 plus P3. As I said, these are scalars. You just add them, and this is equal to 32.14 kilowatt. And Q total is equal to Q1 plus Q2 plus Q3, and this will give me 23.55 kVAR. Once I know P and Q, then I can find S. Okay, so my S as a magnitude is equal to, or this is S total, P total square plus Q total square, again from the power triangle. Everything here is from the power triangle. And this is will equal to 32.14 for the P square plus for the Q, it is 23.55 square. And this will give me total S equal to 39.84 kVA. So with this, I'm done with part A in that question. Then we will move to part B. In part B, it says, what is the total power factor? And again here, the power factor is from the power triangle. This is your P, this is your Q, this is your P, and this is your S, and this is your theta. Okay, so the power factor, your power factor is basically, I will call it total, is equal to cosine theta total, which is equal to cosine, what is the angle? It's basically tan inverse of Q total over P total. So this is my theta total. Because tan theta is equal to Q over P. Tan inverse of this will give me the angle. Cosine angle will give me the power factor. So this is equal to cosine tan inverse of Q total, which is 23.55 divided by 32.14. And this will give me, this angle will be cosine of 36.23, which is equal to 0.807 lagging. So that is my total power factor. including all these three loads. Now, why it is lagging? Because my total P is a plus sign. So this will be a lagging. As I said, that is what is expected from any load, that the power factor is lagging. Now, I want to find what is the needed Q, okay, to improve this power factor from this value to 0.95 lagging. So now in part C, I want to improve the power factor from 0.807 into 0.95. So that will be my power factor old, and this is my power factor new. Okay, now, as we mentioned before, that there is a systematic way how to find this. Okay, so then we will have the old and the new. Okay, so we will have P old, which we already calculate as 32.14 kilo. When we say old, means before we do the correction. We call it before or after, doesn't really matter. Old and new, the same thing. So P old is 32.14 kilowatt. Okay, and theta old, we already know it, which is 36.23. And from this, we can find Q old. Our Q old, I don't need this actually for this because I already have it here. But in some questions, you don't know it. So you need to calculate that, which is P tan theta, but now I already have it. I already calculated in the previous step. So this is equal to 23.55 kVAR. So I know the P, the Q, and the theta before, and always you have to know this information. Now, let's see P new. P new is equal to P old, and this is one fundamental understanding of adding the capacitor bank. The capacitor bank will only change the Q, will reduce the Q, okay? But adding the capacitor will have no influence whatsoever on P. So P stays after the power correction as before. So P new is equal to P old, which is equal to 32.14 kilowatt. Now I need to find theta new. Theta new now is what is your desired value. It's also given to you. So your theta new is equal to cosine inverse of the desired power factor, the 0.95, and this will give me 18.19. This is your angle. Now from this, I will find a Q new. My Q new is basically my P new or P old, it's the same thing, tan theta new. So my P new is given, my theta is given, so this will give me 10.56 kVAR. So what does this mean? It means that after I add the capacitor bank, my total Q has to drop from 23.55 to 10.56. And because Q comes with a negative Q, then I can find what is this QC that is required in part C. So my QC, and I will have it as an absolute value to avoid this negative sign because it's not needed, which is equal to the Q old or the Q new, doesn't really matter because it's absolute value, minus Q old. And this will take the difference between this and this under the absolute value, which is 12.99 kVAR. So this is how much I need to add as a Q of the capacitor bank so that I can improve the power factor 2.95 lagging. Okay, now once we are done with QC, the question was, what is the C, the value, the capacitance, so that we can achieve this, but the capacitance will be connected in Y. Okay, now the capacitance is bare phase. So now I will have a capacitor bank connected in Y. I found the Q of the three phases together. So the QC per phase is equal to the total Q, whatever QC we found, which is 12.99 divided by 3, which is equal to 4.33 kVAR. So this is the Q of per capacitor. Okay. Now, just as a revision, what is the relation between the Q and the C? Just we'll revise that. So if you have a capacitor, okay, we have a current I, we have V, and the ZC is equal to 1 over omega C as a magnitude. We know that the Q of the any Q is equal to VI sine theta. Let me have it again as a magnitude to avoid absolute value, to avoid any minus sign. Okay. Now for the capacitor, because the angle is 90, Q of the capacitor specifically is equal to V times I, because sine theta will be 1. Okay. Now again, this is absolute value because Q will be a negative sign. I don't want to deal with a negative sign here. Okay. Now, using Ohm's law, that we know that I is equal to V divided by 1 over omega C, which is equal to V omega C. This is your I. Substitute here. Then your QC will equal to V squared omega C. This is bare for every single phase. Okay. Now, so from this, your 4.33 is equal to, this is your Q. Now I want to find C. This is equal to V squared times omega times C. What I want to find is actually my C. So my C is equal to 4.33, and I will multiply it by 10 to the power 3 because it's a kilo here. I have now to use the SI units. Now, V squared, I will leave it like this. And omega is the frequency. We already given that the frequency is 60 hertz, but omega in radian per second. So this is 2 pi times 60. So we are left with V squared. Now, V, that will be the phase voltage. This is the voltage that we want to have. Because now, remember, this C is for the phase. We found Q of the phase. Okay, so the voltage of the phase, since this is a Y connection, then my V will be the line to line voltage divided by √3. So your C will equal to 4.33 times 10 to the power 3 divided by V squared, which is basically equal to the 440 divided by √3 all squared times 2 pi times 60, and this will give me 178 microfarad. Finally, what is the current before and after? Okay, very simple. So this is my part E. This is your part D. Now we will use this formula. Total S is equal to √3 V line to line times I line, because I want to find the I line. I want only to find the magnitude. Okay, so the formula will be I line is equal to S divided by √3 V line to line. Now, before I add the capacitor, that I line will equal to S. I already have it. I already calculated S before, 39.84 kVA. So I already have this. So this is equal to 39.84 times 10 to the power of 3, okay, divided by √3, and the line to line voltage is 440, and this give me 52.28 amps. So this is the current that is coming from the source and feeding all these three loads. Now after, same formula. Now in after, we calculated actually the P new, which is the same, and we calculated the Q new. Okay, so we need to find that new S again. So this is straightforward. So your I line will equal to the square root of the p square, 32.14 square, plus the q, which is 10.56 square. I use the q new to find the s new divided by root 3 times 440, and this will give me 33.83 times 10 to power 3, because this is everything times 10 to power 3 here, kilowatt and kVAR, divided by root 3440, and this will give me 44.39 amps. And this what we know about the theory of this, that when I add a capacitor bank, I improve the power factor, and one of the advantages I get is that I will be able to reduce the line current. Okay, now the second question that we have here is a magnetic circuit. And in this magnetic circuit, we are given the dimensions. Usually you have the dimensions so that you can find the L and the cross-section area. As we will progress, we will see how we'll do that. And you are given the permeability, and you are given here in this question the current and the number of turns. And this is very important piece of information. This is the link between the electric circuit and the magnetic circuit. This is why the name electromagnet. It's a coupling between the two. You have an electric circuit that we have the current I, and this I is actually producing the flux that is produced in the magnetic circuit. Okay, so here in this question, we are given all the dimensions. You are asked, what is the flux in the air gaps? So we have here two air gaps, one to the left and one to the right. So we want to know what is the flux, basically, that comes here, and the flux comes here. So I will call this, let's say, phi 2, and this is phi 3. Now, before we solve these type of question, it's very important to know how many different fluxes I will have in this circuit. Why is that? Because this will help me to decide how many circuit branches, the equivalent circuit for this magnetic circuit. Because once you converted this magnetic circuit successfully to an electric circuit, the problem becomes a very trivial, easy circuit problem where you can use your KCL, your KVL, voltage division, current division, any technique that you are comfortable with. There is no restriction. What is the technique that you should use? But the key point here, I want to find this equivalent circuit. So the first thing, you have to understand the operation of this and what is going on. So basically here we have a coil in the middle leg. So basically I will have a flux, okay? And using the right hand rule, my four fingers will be pointing towards the direction of the current, and my thumb will be the direction of the flux. So I will have here a flux, phi 1. And we know that the magnetic circuit somehow behaves like an electric circuit, and the flux basically specifically behaves like the current. So you have a flux going through a branch, and we know that the flux here is the same as the flux there. It's the same flux. But then it will see a junction, or see a node, or see two different paths. So then the flux will be split. Flux to the right, this is what we call it phi 2, and flux to the left, we call it phi 3. Now this will continue here. They will cross with the same magnitude. They will cross the air gap, okay? And then they will, will be your phi 2, and this will be your phi 3. They will combine and then to phi 1, and so on and so forth. And we'll keep doing this. So now I realized that this magnetic circuit will have three branches because we have three different fluxes. That is a key information. Then I want now to start drawing the equivalent circuit, because as I said, that is the key point here. We start from the coil. Where is the coil? It's in the middle. So that's my coil. This is my coil with the current will give me my MMF, magnetomotive force, my equivalent voltage in the circuit. So we'll start here in the middle, and I will have my MMF. Now this MMF, I know its value because this MMF nothing is equal to nothing but N times I. So I know N, I know I, so it's a 300 ampere turn. So I know its value. Now this flux basically is going through all of this, is going through a magnetic material. And it's going through one magnetic material, no different materials. It's going through same material and same dimensions. There's no change in the dimension in the path from the beginning to the end of that middle branch, and there is no change in the material, so it is only one reluctance. Okay, I will call it reluctance 2. Then we will have here the node, branch to the right, branch to the left. Okay, so let's start with go to the right here. Now, the we have here, as you can see, that the material has exactly, although the graph looks a bit misleading, but the width is the same everywhere. It's all 10 centimeter. So we have exactly the same material, and the depth is always the same thing. It's 7 centimeter. So the cross-sectional area doesn't change, but we have an air gap here. So we have two materials, the magnetic material and the air gap. So that means that we will have two reluctances, which is here reluctance 3 and gap 2. And here we will have our flux 2. Okay. Then we go to the left, we will have the same thing. The only thing different here is the difference in the air gap, as we will come here. So we will have here two reluctances as well. This is reluctance 1, reluctance gap 1, and here is my flux 3. And here is my flux 1. That is the most important thing in that question, is to find the equivalent circuit. The rest becomes very, very easy. Now, this is a circuit that I know its voltage. So if I know the resistances, or here is the reluctances, then apply KCL, KVL, I can find all the fluxes. What I want to find? I want to find the flux in the air gap, so flux 2 and flux 3 at two different conditions. First, when the relative permeability of the core is equal to 2000, this is mu r, or when it is infinity, so this is also mu r. So under these two conditions. Okay, so what is the reluctance? The reluctance is basically is an L divided by mu 0 mu r times the cross-sectional area. So we want to find all the reluctances of 1, 2, and 3, and we want to find the reluctance of the air gap 1 and 2. That's all. So let's start with reluctance 1. So we'll have L. Now, what is this L? Let me change the color so that we can explain it in a better way. So let me change the color here. Okay, so L starts from the point that the flux is starting. So this is L going all the way until it reaches its end. Now, at this point, you will start have a different flux. So phi 3 starts from this point. I will call it point A and terminate at point B. And then we have different fluxes. So this is my L. And we would, when we want to find L, we start from the middle of the magnetic material. Not, we don't take the outer or the inner path, but the middle, the average between the outer and the inner. So basically, this will be the middle. So we will have and the middle here and until the middle here. So we will have from this side 5 centimeter and from this side 5 centimeter, and the 30 stays as it is. So from the top part, we have 40 centimeter. From the bottom part, because of the symmetry, we have also 40 centimeter here. Same thing. So 40 and 40. Now to go to the left side here, we will have again from here 5, from here another 5, and again 30. So this is total from here to here is basically 40 centimeters. So we have 40, 40, 40. So this is 120 centimeter or 1.2 meter. That is my L. So let me go here. So this will be equal to 1.2. Now, there is an air gap. Okay. So let's just, although it's a very, very small value, it doesn't really have any impact, but I would recommend you to do that, to subtract this. This is equal to 0.0005 because I'm converting 0.005 centimeter into meter. Everything has to be meter. Divided by mu zero is a constant that will be given to you 4 pi times 10 to minus 7. Mu r, we are doing part A, so it is 2000. And A, the cross-sectional area. Now the width is 10 centimeter or 0.1 meter, and the depth is 7 centimeter or 0.07. That's it. These are all dimensions, and this will equal to 68.2 times 10 to the power 3 ampere turn per Weber. Okay, so this is your first reluctance. Now let's go to do reluctance 3, which is the image of it, which is very similar to it. The only difference is the air gap. Here it is 0.05 centimeter. Here is 0.07. Everything else is exactly the same. So I don't need to show this because it is like an image for it. So it is 1.2 minus 0.0007 divided by 4 pi times 10 to minus 7. Now this doesn't change. 2000.1.07, and we will get almost the same number because from 0.0005 to 0.0007, and if you don't even include it, you will get the same number. So it doesn't really have a big impact. Okay, now we are left with the middle. Okay, so let me change the color again here so that you can see it clearly. So let's go to the middle. Now the middle, again, phi 3 will stop here, start here. Phi 1, this is your phi 1. So this is your, basically your dimension, which is the 40 centimeter. The 5 here, 5 at the bottom, and 30 in the middle. So basically it is the same thing that as we did before, but now we have 40 centimeters. So your R reluctance 2, which is the middle, equal to 0.4. Now there is no air gap here, so I not subtract anything. Divide by exactly the same thing. All magnetic material will have exactly the same thing as far as we don't change the cross-sectional area. So it's 4 pi times 10 to minus 7 divided by 2000, 0.1 times 0.07, and this will give me 22.7 ampere turn per Weber. Okay, so what we are left with what? We are left with RG1 and RG2, the air gaps. Okay, now in the air gap, what is difference here? We already know L. Okay, it's already given to us. And mu R is equal to 1. Because for air, the relative permeability is equal to 1. Okay, so let's go here and you will find RG1, which is basically, let me redraw this here so that we can follow exactly what we do. So here it is, of course, the symbols, you can have any symbols, doesn't really matter. I mean, where is R1, R2, doesn't really matter. MMF here, and then we'll have here reluctance 3, reluctance RG2, And here we will have the other two reluctances which are in series, which is R1 and reluctance RG1. This is my phi 1. Here it is my phi 2. And this is my phi 3. So reluctance of gap 1 basically is equal to 0.0005 divided by 4 pi times 10 to minus 7, which is mu 0 times the cross-section area, which is the same as the magnetic material. We assume that the flux is basically going uniform, the flux that moves here. So it is the same flux like that. In reality, I mentioned that before, the flux goes like there's a fringing effect. But here we are ignoring this. So if we include the fringing effect, there will be a little bit increase in this cross-section area, and that will be stated clearly in the question in case I ask you to take care of the fringing effect, which will be like 1-2% increase in the cross-section area. No big deal. So this is why most of the time we just ignore it. Times the same cross-section area from the previous question, 0.07 times 0.1, and this will give me 56.9 times 10 to the power 3 ampere turn per Weber. Finally, reluctance Rg2 is equal to 0.0007. That's the only difference for this reluctance in the air gap, divided by 4 pi times 10 to minus 7, 0.07 times 0.1, and this will give me 79.6 times 10 to the power 3 ampere 10 per Weber. That's it. Now we already used our knowledge in magnetic circuit to construct the circuit. Now, what is the left is basically circuit, nothing else. Okay, so how to solve it? You have three unknowns. You have phi 1, phi 2, and phi 3. Okay, then you need three equations. So you need one KCL and two KVL. You can solve simultaneous equation if you want, or you can do some circuit reduction. So for example, I can have this. Now this branch and this branch, they are in parallel. So I would do the following. I would have my reluctance 2 here. This is my phi 1. This is my MMF, which is I know. And then I will have here one reluctance only. I will call it reluctance. Maybe I will call it reluctance T. Okay, now reluctance T here is basically reluctance 1 plus Rg1, and this is in parallel with reluctance 3 plus reluctance G2. So this is your total reluctance. So what is your phi 1? Your phi 1, the flux in the middle, is equal to your MMF divided by the reluctance 2 in series with reluctance T. Okay, now your MMF is N times I, which is 300 times 1, number of turns times the current, divided by the reluctance number 2, which we already calculated that before, which is equal to 22.7 times 10 to the power 3, plus this total reluctance is equal to, after you add and in parallel, is equal to 67.7 times 10 to the power 3. And from this, you will find your flux phi 1 is equal to 3.32 milliweber. These are the typical values of the flux. Now I found phi 1 here. I want to find phi 2 and phi 3. Now it's up to you. You can use current division. You can use KVL as well. So if I take a loop here to find phi 2, apply KVL here. So phi 2, which I don't know, times reluctance 3 plus Rg2 minus MMF, this is plus minus, passive convention. This is plus, minus, plus, minus. When the flux enters, it starts with a positive. So plus phi 1, which I already know, times reluctance 2, which I already know, is equal to 0. So everything is known to me except phi 2. Okay, so my phi 2 is basically equal to the MMF minus phi 1 reluctance 2 divided by reluctance 3 plus reluctance G2. We have all the values. Then this is equal to 1.52 milliweber. Okay, what is left? Well, we are left with flux 3. We can apply KCL. Phi 1 is equal to phi 2 plus phi 3. What I want is phi 3, which is equal to phi 1 minus phi 2, which is equal to 1.8 milliweber. So let's go back to the original question. We want to find the flux in each air gap when the relative permeability of the core is equal to 2000, and this is the circuit we did. Okay, now what will happen if the relative permeability becomes infinity? Now we know that the reluctance is equal to L over mu 0 mu r times A. Now for reluctance 1, reluctance 2, and reluctance 3, you will have certain L, different L's, divided by mu 0, but we will have here infinity times A. So this becomes equal to 0. So the only reluctance you will have is basically the air gap. So now my model will change. I will have here the MMF in the middle, and basically we will have only two reluctances, one to the right and one to the left. You will have reluctance G2 here, which I already know because this will not impact its value. Having an infinity or permeability equal to infinity, that does not impact RG2, which is because dependent only on the air gap, and we'll have RG1. So we'll have here your two fluxes, your phi 2 and your phi 3. It's very straightforward that now in part B, your phi 2 is equal to your MMF divided by reluctance G2, which is equal to 3.78 milliweber. We already did that. We know the MMF, we know the RG2 from the previous part. And phi 3 is again, because they are in parallel, MMF divided by reluctance G1, and this will give me 5.27 milliweber. If I ask you to find phi 1, I didn't ask you in this question, but if I did, it's basically phi 2 plus phi 3.